welcome back. This is yet one more video where we teach ourselves the electrical engineering, the electric circuit diagram language that we need to understand electrical signaling in neurons. In this video, we're going to look at energy sources, namely the voltage source and the current source. Often when we talk about cells, the voltage or current source is actually the amplifier we use to inject current or voltage depending on the application. So let's start with the voltage source, which you're very familiar with because we use voltage sources all the time, namely batteries. Batteries are one form of voltage source. So the symbol of a voltage source are two lines and they're of unequal length, and that's important once we also add capacitors to our diagrams. So this is what it would look like. A voltage source gives you a predefined amount of voltage. So as always, we can write V here between the 2 points, between two ends. And so for example, a AA battery would be 1.5 volts and so on. Now, this is constant voltage. So it's not like the voltage from the electric outlet, which is actually alternating. This is just constant voltage at a given value V. So what is the current? Because in these type of circuits and the type of questions and models that we use to understand electrophysiology, we always want to understand how voltage and current relates. So what is the current? The current, and by the way, we draw it of opposite sign to the voltage and only for the voltage source. And that's because, it's a long explanation, but in essence, this delivers energy versus resistors and capacitors dissipate energy. So that's why it goes the other way. But you can just memorize it that way and you'll be fine. So how does that relate? Well, the voltage is given. The current can be whatever it is based on what resistor or what circuit, or in more general terms, what load or what impedance we attach to it. And if you have questions about the resistor, there's a separate video on resistor and resistance that I encourage you to check out. But let's assume we have a resistor here, R. So the voltage here across the resistor is the same as the voltage across the battery. Kirchhoff's law, you go once around the loop, it should be 0, and there's no branch point, so we know it's current I everywhere. We use what is called Ohm's law to describe this. So voltage equals current times resistance. So V is given, that's on the label of your, and by the way, those are not real circuits you would build like that, so these are all just theoretical ideas. So V would be the label on your battery, how many volts, and depending on how big or small the resistor is, the current will change. That's Ohm's law. It is interesting to think about two extreme cases, and they're theoretical, and you should never do them as a real circuit, because one of them is dangerous. So the non-dangerous one is to say, well, let's make the resistance really, really high, or as a mathematician would say, goes towards infinity. That is essentially as just the same as just having the voltage source and nothing else, nothing connected. We're assuming that the two ends are in air and that the resistance of the air is so high that no current passes through, which is a pretty good assumption. So that's your battery, you just hold it in the hand and there's no current flowing. The opposite that you can also consider, and this is theoretical because this would be dangerous, so don't do that at home, is to make the resistance 0. That is called a short circuit. So the dangerous circuit would look like this, just the ends connected. So don't do that. What happens here? Well, the resistance is 0. So an infinite amount of current can flow. And remember, the voltage source tries to generate the voltage it's supposed to generate. So if you look at, again, V equals IR, we know now R is 0. So to get to the voltage that the voltage source promises us in the label to deliver, the current would have to be infinite. Of course, first there is an accident or an injury or something melts, because that's what a short circuit is. Why do we care about these voltage sources? We care about them in the context of neurophysiology because we can use them to model certain manipulations we do with our amplifiers when we measure and perturb the electric state of the cell. We also actually use voltage sources to model the force that moves ions across the membrane, which is caused by the difference in ion concentration inside and outside. That's where voltage comes in, or voltage sources. I hope this has helped to better understand what a voltage source is and how to think about how much current would actually flow. In the next video that I encourage you to look at, we'll look at the twin of the voltage source. It's called the current source. It's a little bit less intuitive, but it's super helpful to understand when we want to understand how neurons process information through electrical signaling. Till then, take care. Bye-bye.